Our next talk is Simple is Best, the journey of taking over a mobile system using a GPU logical bunk. And it's my pleasure to introduce our next speaker, Shang Hongze, a senior security researcher at Dawn Security Lab. Shang specializes in Android security, virtualization, IoT security, and mobile protection techniques. He's also an experienced CTF player, formerly the captain of the 6 Stars team, and a DEF CON CTF champion with AOE. Let's give a warm welcome to Shang Hongze.
Hello everyone, I'm so excited to be here to talking about a GPU bug I found last year, and I use it to take over control the mobile system. And before start, let me introduce myself. My name is Shang Hongze. I'm a senior security researcher from Dawn Security Lab, and I was also a CTF player, and we won the DEF CON CTF in 2020 as a member of AOE. And recently, I'm focusing on the Android security, IoT, and Windows. And our security lab, the work of our security lab is mainly focusing on the mobile security and anti-advertisement fraud and robot clicks. And we also won the Pioneer Award in 2022. And here's a Twitter, and don't hesitate to follow it. So let's begin. Here's the agenda of today. And firstly, I want to introduce the background, why we need the root. And then I will introduce the Android GPU. And thirdly, I will introduce my bug hunting and how to exploit it in Huawei's latest SoC named Qilin. And the last is a demo show. So why we need the root? I think most of us think it's pretty cool because we can start our bug hunting and got the big bounty from the vendor, and it also can be controlled we can also control everything, and it's helpful for our debugging and developing. The most important for us is to see everything, because our major work is about anti-mobile advertisement fraud. So there are so many bad cases in the real production environment, like traffic hijacking and robot clicks. So what is the traffic hijack? So let's take a view. So in this case, we opened here's a bad case about the input master application injection. We opened our application to search some products because we want to buy it from our application, but the user doesn't touch the searching button, and it redirects to a new page with some reference link. So it's called by the input method because they knows what the users really want to buy, and he quickly generates advertisement and trigger the user to open it automatically. So if the user purchases the product from this page, and Jingdong will pay a promotion fee to him, but it's not really advertisement because in normal case, we want to attract user from outside of our application. So it's a malicious event. So how do we find this? That's why we need the root. Because when we have a root, we can break through the sandbox protection, and we can extract the local files from the test devices and located the evidence of malicious applications or some bad rooms. So let's introduce the Android GPU. I think the Android is complex, but simply it almost equals the Android framework and the Linux kernel and the HAL. HAL means hardware abstraction layer. It's a unified interface for different hardware. In this case, we our developers don't know which platform their applications run. So Android just use a unified interface. It consists of two parts: the shared user library and it's running on the Rin3 world, and the kernel module it runs in the Rin0 world. So here's a case about a normal GPU rendering. So when we start the application, and if it wants to show a picture, and firstly it will look up the system shared library from the system rooms, and because it poses the same function from all rooms, so it's easy to link it and load it. But the shared library will be different in different mobile. For example, if the mobile is Snapdragon, and it will register the character devices like KGSL 3D0. So when we open the character device, we just open the GPU context. So Rin0 world's code is very dangerous, and also Android knows it. So if we can send some illegal syscall sequence directly to the kernel module, we just skipped the shared library, so it's a big attack interface. So Android just limited the access of all the HL kernel module. And for example, there is two kernel modules in this picture. The first is the GPU kernel module, and the second is a camera kernel module. And if we dump the SE Linux ruler set and just parasite, we can see, as we can see, the video device is only accessed by the system process, so we can't directly open the camera if we are a normal application. But the GPU is different. GPU is, as we can see, the GPU is accessible for everyone. So if we, because we are the untrusted application, so we can directly open it and send the L control or IMAP. So this is why we choose the GPU as our research target, because the attack interface is exposed to the normal application. Here are some bugs in the wild and exposed by Google Project Zero. And as we can see, there are so many GPU bugs in recent years, and almost all of them is page UF or race condition, and the exploitation is stable and faster, and it's very powerful to achieve the local privilege exception. So let's take a view about the Huawei SoC. Here's my target. My mobile phone is Huawei Mate 60 Pro, and it was launched in the 2023, and the kernel driver is also open source, so we can download from here. But what surprised me is that there is no public bug report online. So I just start my analysis. If we download the code, and we can see some similar, like Mali's kernel driver. And first, in this case, we can simply use this C code to interact with the GPU kernel module. Firstly, we open the device characters, and then we use IO control to init the GPU configuration. And in the last, we can allocate a GPU memory using a special IO control command, and just send them with special argument, and it will return the correct value if we correct the args. So here is some special GPU memory block in Huawei's SoC. As we can see, for example, the first is GPU memory. GPU memory means it will allocate a normal GPU memory, and it won't be shared with the CPU process. And the second is the SIM virtual address. SIM virtual address means it will be always shared with the CPU process. So we can map it to the user space and use the CPU to directly access. And luckily, today's bug is only use the virtual address. So let's take a view. Before I start, I want to introduce the. Let's take a view about the allocating function. So to ensure the GPU virtual address areas doesn't overlap between each other, and most of kernel module use RB tree to maintain the GPU memory list. For example, the Snapdragon and Mali use it. But in Huawei's SoC, they use Linux virtual memory management API. So let's take a view. So when we allocate the address, it will call VM map. So it's very convenient because the Linux kernel will make sure that there is no two memory block will be overlapped. But and in this case, if we want to share our memory with CPU, we just set the proto flags with the VM read or VM write, and if we only want to allocate a memory and only be accessed by GPU, we can clear these flags. So the GPU SIM virtual address alloc function just like this. Firstly, it will be allocate the real physical page using the alloc HVGR alloc page. And secondly, it will be allocate a new VMA entry and using the VM map. And in this function, it will also set up the CPU page fault callback if it is shared with the CPU user space. And lastly, it will be set up the GPU page table entry. So the GPU is very similar like the CPU, and it uses the virtual address and the physical address to management different GPU contexts. So let's take a view about the free function. Firstly, it will be clear the GPU page table using the mmap GVA. And secondly, it will call the VM mmap to release the VM entry. And finally, it will release the physical page. Seems it's very, very simple, but there are things I found is very interesting. So they just ignore the return value and force it using the void. So why we need to ignore the return value? Let's take a deep view. So in the same way virtual address, same way free function, the free way means it will release the VMA entry, and here the backtrace. As we can see, the same way free function calls the VMI map, and it just ignores the VMI map return value. So what if the VMI map return value failed? So here's the thing. If the VMI map failed and the CPU page table entry will be not cleared, and but the physical page has been freed. So maybe there is a page OF. So how to make the VMI map field? I think there are two cases. The first is we just pass the invalid address or length to the function call. But in this case, it might impossible because the args is the GPU memory. And another case is to trigger a VMA split event if the address is misaligned, and it will be go to fail because if we can spread the user space with many memory segments, and if the total VMA count larger than the system configuration, it will be go to fail. It will go to fail, and the second is we can map a special memory and with a special flags, and it tells the kernel that I can't be splitted. But in fact, the GPU memory address is always the range of the VMA entry. So for now, I think the VMA entry will be the VM call. The VMI map will be always returns true, and I struggled it for a few days, and in the final, I found some more interesting things. First, in the kernel model, we call the VMI map to alloc a virtual address in the CPU user space, and also it just equals we can use IMAP to call it in the user space in the user space, and if we release the virtual address using the IMAP, it equals the VMI map in kernel mode. So because we alloc the GPU memory using the VMI map in the kernel mode, and we can also directly free it in the user space. So here's the thing. Firstly, we alloc GPU memory using I/O control, and we just release the VMA entry using the IMAP syscall. And then we release the GPU memory using the I/O control. In this case, the VMI map does return to the false, but the CPU page table entry will be also cleared, so there is no more page UF. So we must figure out a way that we can keep the CPU page table, and we also want to the VMAP field. So after take another functions, and after I take a view about the other functions, I found some interesting things. Before I introduce it, I want to explain the the argument of allocating a GPU memory. So here are the two important arguments. The first is the page. It means the GPU wants allocate a real the count of the physical page. And the second argument is the max page. It's the GPU virtual memory address. So if we pass the page to 1 and the max page equals 2, and just like this, and we allocate two virtual page address, but indeed we only allocating the one physical page. There's another function named resize, because if we want to increase the physical page, we can directly directly call the resize function with the older GPU virtual address and the new page size. So it will be it will allocate a new physical memory and set up the GPU page table entry, and if it mapped, it's mapped in the user space, it will be also set up the GPU page table. So in this case, we can rewrite the CPU page table entry again, even if we unmap it from the user space. So let's put it together. The exploitation is just like this. Firstly, we allocate a GPU memory using IO control, and we set the page equals to 0 and the max page equals to 1. And when we just allocate a virtual address, and there's no physical page used. And secondly, we just quickly unmap the CPU virtual address and unmap and using the syscall map to allocate a larger memory segment, and it should covering the GPU virtual address range. So because we want to release it from using the L control, and it will be filled if if the CPU virtual address is misaligned with VMA entry. So thirdly, we can call the reset function and allocating a real physical page, and the CPU page table and the GPU page table will be filled in this time. So just like this, the CPU virtual address is misaligned, but it doesn't check it's the GPU it's a GPU virtual address. So it will be the page table of CPU will be also filled. In the last, we free the GPU memory using IO control, just like the left. The first is unmap the GPU virtual address. It will be true. And secondly, we free the virtual address using VM map. But in this case, we can trigger a VMA split event, and it will be go to false. And the CPU's page table entry will be not cleared. And finally, we release the physical page, so which achieves the page UF. So also we can make it fast and stable, because we can directly allocate 1 GB physical page, and so there's 1 G memory we can spray, and In this case, S3 it's using the CPU page table entry and just searching and using the KSMA attack technique to achieve the write from the attribute physical address. And Huawei's kernel text lands on 10000 in hex mode, so we can just searching the kernel context and searching some special structs. And in the final, we can rewrite the system read-only file to achieve the local privilege exception. So what can we do? In this case, we can rewrite the run as binary because it's a field in the system rooms. And when we patching it, we can switch to other users. And we can inject shellcode to the privilege process, but HKIP still works, so we can't disable the SE Linux, and patching the kernel code will be crash the system. But don't worry, I think we can learn it from the next speech. So here's the demo. The mobile is a Huawei Mate 60, and the security patch is the last year. So let's take a view. Firstly, we want to check the system version. As we can see, it's a last year's patch. And we just open a normal application, and the identity is very normal. And then we exploited it, and we got the system shell. So we can also see the kernel version, and we can also directly close it and kill the application. And the system will be stable, and just nothing happened. So it's a very fast and stable exploitation. So let's see how Huawei fixed it. When I see the patch, I found it's surprising because it doesn't patch the root cause. It just patches a function that I use to exploit. In this case, it adjusts the reset function, and if we reset the same virtual address memory, it will be denied. So if the CPU memory and the GPU memory shared, we can't reset anymore. So the IMAP still works, but we can't rewrite the CPU page table entry after we call the IMAP. So there's no more page UF. So thanks for your listening. This is my talk.
Thank you, Hongze, for the interesting presentation. I'll now be opening up the floor to any questions from the crowd.
Thank you for a really interesting presentation. Your test, this was done with what was it? I forgot now. The Huawei Mate 60 Pro.
Yes.
Kirin SoC, but with Android OS, right?
Yeah.
Have you done anything with Harmony OS?
No. Harmony OS, as far as I know, the latest Harmony OS just different architecture of the GPU kernel module. It separated as a single process and limits his permission to others to systems. It just limits the permission to for the GPU process. There's no attack interface like this in Android.
You mean how many OS does not have this same attack
Yes.
surface?
I think it's more secure for users.
How many OS is more secure? Is that what you mean?
Yes.
Okay, thank you. Thank you.
Are there any more questions for Hongze? If not, please join me in giving a big round of applause for Hongze for their interesting presentation.